Okay, today what we're going to start talking about is what does the definite integral mean in the context of a word problem. So we already learned what it means geometrically. So this definite integral, remember this is called a definite integral because you have bounds. So remember if I give you a graph, if this is, let's say, f of x, the bounds would be your x values from a to b, your f of x would be the y value, and then your dx would be the width of the very small rectangle. And what this integral symbol is saying is, remember we talked about that is you're adding up infinite number of rectangles. So we call it a limit of sums. So that's what it means geometrically. We're adding up an infinite number of rectangles from A to B to try to get the exact area underneath the curve. Okay. Now let's first talk about units in context of word problems first. Okay. So let's say I give you a definite integral. And I'm going to tell you that f of t represents the velocity of a function, and the units on f of t are meters per second. Okay, so this is going to be meters per second. dt is the very small change in the time interval. So the time interval here is seconds, so that would be seconds. So what you're doing is you're multiplying meters per second times second. So notice that the seconds drop out and you're left with meters. Now the integral symbol doesn't change your units. All it says is you're adding up a whole bunch of meters. So all we still end up with is meters at the end. So when you take the antiderivative of the velocity function, your final answer is going to end up being meters, which actually represents the position function. And if you think about what we learned before, remember we learned that if you start with the position function, the derivative of the position function is your velocity function. Now we're going backwards. If I give you the velocity, I'm going to ask you to come up with if we take the antiderivative velocity, we end up back with the position. So that's why when I take the antiderivative of the velocity function, we get back to position, and that's why your units end up being meters. And the same idea is going to happen with, let's say I give you acceleration. So let's say f of t is measured in meters per second squared, which would be units for acceleration. So this is meters per second squared. dt is still seconds. So notice one of the seconds drop out, and your final units would be meters per second for this definite integral. But same idea, if we go from velocity and take up my derivative, I will get to acceleration. But if we go the other way, if I take the antiderivative of acceleration, which is what we're doing here, then notice we end up back to velocity. Okay, let's try one that's not a motion problem. Let's say f of t is measured in dollars per year. So it just represents a function, it measures dollars per year. So f of t would be dollars per year, that's the units. Your time interval, your dt, is dollars. So we are multiplying here by years. Your time interval here is years. And notice what happens. The years will drop out. So the units for this definite integral, if f of t was dollars per year, would get me back to dollars. Okay, so now what this is going to lead to is this next idea here. So notice we started with the rate, dollars per year. And then the definite integral leads me to just the dollars. So the idea is if you take the antiderivative or you take the integral of a rate, then what you end up back to is the value of that y value, or sometimes I call it the population. So instead of dollars per year, let's say you integrate population per year. Then when you integrate that, you will end up with total population. And that's what this next piece here, this what's called the NetChange theorem is talking about. So let's go back just to notation. So again, this is our definite integral. So if we take the antiderivative of f prime, right, and I go up, that will lead me back to f, right? So the fundamental theorem tells us that if I have bounds, I take the antiderivative, which in this case would be f of x. So let me do this step here. and then we plug in the upper bound, and then we subtract off the lower bound. So this is just general definition of the fundamental theorem. Okay, so for contextual situations, what we can say is if you integrate the rate of change of a function over an interval from a to b, you will determine the amount of change in that function in that time interval. So the idea is this: if you integrate, let's say P of t is a population. If P prime is the rate at which the population is changing, when you integrate that, you're going to take P of t of 2 minus P of t sub 1. So that this will give you the net change in the population between the two times. Okay. Okay, so let's look at a one example, and this will make a little bit more sense. So this is the net change theorem again. Okay, so let's say the initial population of a town is 5,500. The population is changing at a rate of P prime of t. Okay, and I want to determine the population from 0 to 10 years. So the idea is if I take this antiderivative, the units for this is population per year. Units on this is per years. So antiderivative P prime is going to be P of 10, right? Antiderivative P prime is P, and I will subtract off the lower bound. So notice the antiderivative of that rate gives me the change in the population from year 10 to year 0. So if I want the final population at year 10, which would be P of 10, I can just move this P of 0 over, and this would be another way to write this. So the idea is this gives you the net change in population from 0 to 10 years. If I add the initial population at time 0, that will give me my final population at time 10.